to today's lesson. Today we're going to be looking at graphing sine and cosine and some of the key components of these graphs. Now, just to warm us up, I'm going to look at graphing another function, something you might remember. When we graph a function like y equals x squared, what is it we're actually doing? Well, we're taking the collection of points from a table of values, things like if x is negative 1, squared is 1, if x is 0, squared is 0, if x is 1, squared is 1, and so on. And we go to an xy grid, and we plot these points, and it creates our picture. And I'm sure you remember that these points make a parabola. Okay. Now, when we go to graph sine and cosine, they are functions as well. But instead of y equals x squared, we're going to be looking at y equals sine of x. And that is a trigonometric function. And we could create a table of values just like these ones, except that we're probably going to find certain points are more beneficial to us than other points. So let's just clean up our table a little bit and have a look. So the logic's the same. I'm really doing the same thing that I'm doing here, but I'm doing it for this trigonometric function. So let's start off with, what if we put in 0 degrees? 0 degrees, if I work that on a calculator, well, the sine of 0 degrees is 0. Now, I could put in 1 degree, 2 degree, 3 degrees and find corresponding y values, but we will see very quickly that that's not going to create as good a picture for us as if we went to certain key component, or what I like to think of as sort of junctions in the graph, nodes in the graph. A really important one is 90 degrees, and the sine of 90 degrees is 1. 180 degrees is the next important node, and we find that the sine of 180 degrees is 0. And we could keep going like this. Now, we're only going to start looking at the graph up to about 360 degrees, so I'll just finish off my table. So we have these as our kind of very important junctions or nodes in our graph. Now, what are they going to look like? Well, if we go ahead and we graph these, and have maybe just enough room at the bottom here. Okay, here's my x and my y-axis. And because I'm going from 0 to 360, I'm going to make this the 360 over here. Give myself a little bit of working space here. Halfway through is 180. And then halfway through that is 90 and 270. Okay, and I can see that there are certain y values. It seems to go up to a 1, and it seems to go down to a negative 1. So what I now have to do is plot these important points. We have 0, 0, 90 corresponds to a 1, 180 corresponds to 0, 270 corresponds to negative 1, and 360 corresponds to 0. Now remember, I could have put in 1 degree, 2 degrees, and all the various numbers in between, and that's essentially what a graphing calculator does, is it plots all the points in between and creates a picture. So this is what I would get if I would do that. It goes up like this, and then oscillates down like so. Now, that is our first look at the sine function. And there's a couple of important things to note here. First of all, we see a maximum value of 1. So I'm going to make some of these observations over here. Maximum value is positive 1. Minimum value is negative 1. But what's more important, instead of referring to maximums and minimums when it comes to trigonometric functions, is something we call the amplitude. Now, the amplitude a way of thinking about the amplitude is it's kind of the distance from this middle line, which in this case is the x-axis itself. Okay, we got the x-axis down the middle, and the distance up to the maximum oscillation, that distance is 1. And if you think of the distance from this middle down to our minimum, that distance is also 1. So what we have here is 1. That distance from this kind of spine of the graph is what we call the amplitude. Now there is a way of calculating the amplitude mathematically, and it looks like this. It's the absolute value of the maximum minus the minimum divided by 2. And you'll see what happens here if I put these numbers in. The absolute value of 1 minus negative 1 divided by 2 would give us 1 plus 1, or the absolute value of 2 divided by 2, and that of course is 1. Sometimes it's nice to have this little relationship here, what by definition the amplitude is, in case the graph has been shifted all over the place and it's been stretched and all these various things. But in most cases, you can pretty much just look and say, well, here's the sort of the middle of my graph, the spine of the graph, and I'm oscillating up a distance of 1, and I'm oscillating down a distance of 1. I find usually you can just spot those from the graph. So that's what we call the amplitude. And there's another important feature of the sine graph. And I'll make a little room here for this. This is a feature that's called the period. Now, I'll just clear this off and write that up. What we call the period of the graph is how big one cycle is. Okay, so by definition, it's the length of one cycle. Now you notice my graph only depicts one cycle. If I were to keep going, the graph would continue and repeat. It would be exactly what this is here, repeating from 360 onwards. So I get another oscillation up like that, and so on. And if I were to go to the left and plug in some negative numbers, I would find that it would be exactly like taking this graph and moving it 360 degrees to the left. So I would have a graph going like this, and so on. So one oscillation is essentially from here to there. And that's what we call one period. Okay? Now, in this case, one period is 360 degrees. Not all trig functions have a period of 360 degrees. In fact, not all functions have a period of 360 degrees. I mean, we might get some really strange-looking functions. We could get things that do something like this. This one kind of goes like so, and then maybe it does a little hiccup in the middle, and then it comes from here. And then maybe at this point, it all repeats. Okay, maybe it goes up again, does a little hiccup, and then comes up from down here. So I might make the observation, oh boy, this thing has totally repeated. So this, from here to here, that would be one period. Okay, so it all depends on what function you're dealing with. So that's kind of the important features of the sine graph. What I'm now going to do is look at the other very important trig function, and that is the cosine graph. So, give ourselves a little room, and we're going to look at a few key points or nodes and see what kind of graph we get. Okay, if I looked at, for cosine, table of values, and maybe I'll work over here, and then draw the corresponding graph over here. Okay, well, 0 degrees corresponds to 1. 90 degrees, and again, you'll see I'm going by 90 degrees. These are the important points, corresponds to 0. 180 degrees corresponds to -1. 270 degrees corresponds to 0. 360 degrees corresponds to 1. Now what's that going to look like? Well, we're going to have this point here, 0 degrees corresponding to 1. 90 degrees later, we're at 0. At 180 degrees, we're down at -1. At 270 degrees, we're at 0. And at 360 degrees, we're back at 1. So this is what our graph looks like. So that's the basic cosine graph. And again, we notice a few important features. The amplitude is 1, oscillates up 1, and it oscillates down 1. The period of this graph is again 360 degrees. Now once more, if I continued in both directions, we would find that the graph starts to repeat. Same thing over here. This would be the end of a graph that's basically starting here at -360 degrees. So there we have the amplitude and the period and all the key important points on the cosine graph. Now, what about if we wanted to draw something that has a different amplitude, or we want to change the period? Maybe we don't want it to be 360 degrees. We want it to be 180 degrees and get a complete cycle in, or maybe 10 degrees or something like that. Well, in order to do that, we can make some very simple modifications to the equations themselves. And some of these things we've talked about earlier, such as how do we get a vertical stretch. And that's really what we're talking about when we say changes in the amplitude. So here's how we change the amplitude. Very simple. We can take either the sine graph, or we can take the cosine graph. And you'll notice I'm writing k in front of both of these functions. Remember that if you have some kind of a function, y equals f of x, if you want to stretch it vertically, all you have to do is put k in front of the function. Well, that's exactly what I've done here and what I've done here. I put k in front of the entire trig function. So what it's going to do is it's going to affect the vertical by a factor of k. So for example, if I wanted to graph the following, and let's say I was not going to use a lengthy table of values, but I was just going to try and get a very quick version of the graph. Let's say I had 2 times sine x. All that's going to happen is that vertically, everything is expanded by a factor of 2. So my amplitude is a 2. So what is my graph going to look like? Well, it just means instead of oscillating up to a maximum of 1 and a minimum of -1, it's going to oscillate up to a maximum of 2 and a minimum of -2. So if this is sine, I'm still going to start at 0, 0, and I'm still going to, at certain key points here, like 180 degrees, 360 degrees, I'm still going to be at zeros. But at 90 degrees, I'm not going to be up at 1. I'm going to be double that distance, factor of 2. My amplitude is going to go up to 2. And same thing here at 270 degrees, I'm going to go down to -2. So here's what my graph looks like. Okay. The only other thing that's important here is that you've got to remember amplitude is a distance and therefore is always positive. It's a length. It's how much oscillation is there in a sine or a cosine graph. So never think of amplitude as being a negative number. Okay, one other thing that we have to look at is changing the period. And changing the period, right now it's 360 degrees, but we may want to scrunch the graph up, we may want to stretch the graph out. And if you recall, how do we do that, a horizontal compression or expansion? It was very simple. We took the function and we simply took some number, and maybe I'll call this one q. We took that q number and put it right next to x. And what this did was it affected the graph by a factor of 1 over q. Okay, but it wasn't q, it was 1 over q. It was the reciprocal of that number that is the factor. And so if this turned out to be something like 1/2, we realized that was going to be a compression. And if this turned out to be something like 4, then it was going to be stretched horizontally. So let's look at an example of that and see if we can identify the period and create a function. We might look at something like this. Y equals, maybe we'll do cosine this time. We'll look at cosine, and let's start simple enough. Let's just put in 2x. Now, what we could identify is that the reciprocal here is 1/2. So horizontally, I am expecting things to be affected by a factor of 1/2, which means I would expect the graph to be compressed. But let's find out exactly what the period would be. Now, once I recognize, oh, I'm compressing it by a factor of 1/2, the normal period for the cosine graph is 360 degrees. And I'm affecting that by 1/2, so the new period would be 180 degrees. And so when I go to graph this, all I have to do is make sure, well, I'm going to go and complete the cycle at 180 degrees, not 360. Halfway through there is going to be 90 degrees, and halfway through that is 45. And halfway between 90 and 180 is 135. Now, there's been no change to the amplitude, so there's no change in my vertical expansion or compression, so I'm expecting to have a maximum of 1 and a minimum of -1. This being a cosine graph, it would start at its maximum, then go to 0, then to the minimum, then back to 0, and then returning to the maximum value of 1. So there is our graph. Okay? So that's how we graph sine and cosine, and we change the period, we change the amplitude. One more thing that we have to look at is, what about working backwards? Sometimes you think, hey, I know this stuff, I've seen it, I know it, easy. And what they go and do is we see a question where we have the graph and we have to work backwards. And we have to say, well, how do we get this number, or how do we figure out the amplitude? So let me draw an example of that. See if we can work backwards and use our detective skills and piece together an equation that works. So this time, I'm going to have an equation that looks like this. Okay. Now I'm going to just say that that's 9 and that that's -9. Okay. And this graph, we're going to start here, and it's going to hit its maximum, and so on and so forth. And this time when I finish up, I'm going to say, oh, by the way, that's 90 degrees. Okay, there it is. Now it looks a lot like a sine function, and that's precisely what I think we should use here. Later on we'll learn that it could also be a cosine function, but we're just not there yet. So here's what we have. We're going to have to figure out some kind of an amplitude for our sine function, and we're going to have to figure out some kind of, call it Q, some kind of number that affects the period. Now, I think the amplitude is probably the easiest one to spot. We can see from the middle we've oscillated up 9 units, and to confirm we see over here we're oscillating down 9 units, so we know that this is going to be a 9. Now the only question is, what number do we want to put in here? And here's how I would recommend you do this. We know that this number, which I'm calling Q, works as follows. 1 over Q, okay, the reciprocal of Q, times the normal period, which is 360 degrees because it's a sine function, is the period. Okay, and I look at my graph and say, oh, the period is 90. So that gives me an equation that I can solve for Q. I'm going to multiply both sides by Q, leaving me with 360 equals 90 times Q. And to solve for Q, I'm going to divide by 90. So Q turns out to be 4. So all I got to do now is replace Q with the value that we just figured out, and there's our equation. There's one other thing that you should be familiar with. I've used degrees today because that tends to be what we're the most comfortable with. But you've got to also get comfortable drawing sine and cosine using radian angular measure. So as a last little thing to leave you with, I'm just going to redraw these using radians. And so for the sine graph, instead of going 360 degrees, we would think of one complete cycle, or the period of the graph, as 2 pi. Halfway is pi, and halfway again is pi by 2. So pi by 2 is the same as 90 degrees. Pi is the 180. And over here, 3 pi by 2 is the same as 270 degrees. Now, if we're drawing sine, we want to go and have 0 at both the start and the end, and halfway through. Then it goes up to its maximum, and then down to its minimum. So there's sine using radians. And if we wanted to draw cosine, we would want the same radian breakdown, except instead of starting at 0, we want to start at 1. So we're starting at 1, then going to 0, then -1, then 0, then back to 1. There's our cosine graph. Whoops. Not the best drawings, but those are the important points, even if your drawing isn't quite on the money. And that concludes our look at the sine and cosine graphs for today. Catch you later.